Today's era is one of information everywhere, in which the size and availability of valuable datasets is increasing rapidly, especially in the physical and life sciences. For example, extracting meaningful data from a single human genome involves the analysis of over 3 billion base pairs. Using FPGA-based heterogeneous systems, such as the Convey hybrid core platforms, life science experts can address big data problems common in their field. However, such users often lack the set of hardware design skills traditionally required to develop accelerators for these platforms. Hence, these experts rely on existing accelerators that may not meet unique needs specific to their research. Our approach to this problem, ConVI, is an accelerator development flow targeting the Convey HC-series platforms and utilizing LabVIEW as its front end for control and data flow design. LabVIEW's abstractions lower the entry-level barrier and enable non-engineers to understand and design complex FPGA-based accelerators without the typically required HDL skill set. The Convey HC-1 platform that was used in our work is partitioned into the host and coprocessor. The host features an Intel Xeon CPU and is connected via the front-side bus to the coprocessor board, which contains 4 large Xilinx FPGAs, or application engines. Each is connected to shared memory with a total peak throughput of 80 GB per second. A configuration of the coprocessor is referred to as a personality and is callable by a host C++ application through a custom instruction interface. The standard approach to personality development for the HC-1 platform is to use Convey's Personality Development Kit, or PDK. However, this requires excellent knowledge of Verilog or VHDL, and a solid understanding of parallel processing and memory access concepts, rendering the process unusable by non-engineers. We attempt to break through this limitation with ConVI. Development of an accelerator within the ConVI flow begins in LabVIEW. Keep in mind that in ConVI, LabVIEW is used to develop the coprocessor configuration and not the host application software, though we would like to pursue an integrated solution in future work. To move data to and from the coprocessor, ConVI provides sub-VIs that abstract the Convey memory controller and instruction dispatch interfaces into simplified communication blocks. For example, data can be pulled from the memory interface using a streamer source object, which provides a stream of data words from memory. LabVIEW also helps make it easy to test the design locally. The Convey interface sub-VIs can be exchanged for desktop-compatible versions that operate on controls, indicators, and file I/O, rather than the memory and instruction interfaces on the Convey platform itself. When combined with a C++ host application, the accelerator can be verified in system-wide simulation on the Convey platform, or deployed for actual use. To illustrate the flow, let's walk through an implementation of the Smith-Waterman sequence alignment algorithm. This design is a systolic array implementation, and performs the search by streaming a large DNA sequence through an array of systolic cells. At the top level, we have Convey-specific inputs and a state machine responsible for streaming in the sequence data from memory. The data is passed into a pipeline of systolic cells, and the results are stored using Convey-specific outputs. The processing cell calculates the Smith-Waterman alignment score for every symbol in the reference sequence, and is connected to neighboring cells through a systolic interface. In practice, such pipelines contain hundreds or even thousands of cells, so we created a VI script to replicate the cells and make the necessary connections between them. Here, a small pipeline of 16 cells is generated. After the user has unit tested the accelerator on the desktop, a system simulation on the Convey platform can be performed by clicking Run in the VI window. In this sped-up video, LabVIEW brews up the necessary design files, sends them to Convey, initiates a full system simulation with the pre-written host application, and then connects the LabVIEW front panel to the simulation for real-time visibility and control. To test ConVI's usability and effectiveness as a development flow for bioinformatics applications, we presented the Smith-Waterman design to a group of students at an NSF-sponsored summer program at the Virginia Bioinformatics Institute at Virginia Tech. The students, most of whom have either a computer science or biology background, were given the reference design and tasked with extending its functionality. Following are some comments they had about their experience using LabVIEW within the ConVI flow.
As a biologist and computer scientist by training, and I have no experience with hardware and HDL. And this, from these 2 weeks, I feel like this effort that make LabVIEW a tool that can implement the for FPGA, it's a very good approach. The hardware knowledge I can use LabVIEW as a communication tool to talk with people who really know hardware really well, and really implement my modules that in a way that can run in hardware. So people from the biology or bioinformatics side can implement their LabVIEW implement their ideas in LabVIEW without a very long learning curve. People from hardware side, they don't need to really spend a lot of time trying to understand just what the biologists are trying to do, and this will accelerate the collaboration and definitely will make this development process faster.
Well, at first I was very skeptical because I've been coding for like 12 years, and since high school I'm coding in C, and that's the language that I'll always prefer, and I love it a lot. To realize that LabVIEW is an entirely different, not just a software, it's a programming paradigm. We need to move forward from this serial paradigm to an actual parallel graphical design environment, and I believe LabVIEW has the potential for that.
So, as an electrical engineer by training, I found myself resorting to low-level primitives in the language quite often. And one of the challenges when you're doing that in a highly abstracted language is that some things aren't as well supported as they are when you're writing in the language that was intended for this kind of thing. The things that LabVIEW does very well is illustrate to the user exactly what happens at every time step. Perhaps one of the drawbacks that I found was that the feedback loops absolutely require a register to be inserted, which I found a little bit confusing, to give the user some kind of indication of whether he's reaching the timing wall. I think that would be a very natural extension to the program.
I think that it's very nice environment for actually visualizing the parallelism of circuits and of the complex pipelines. Actually, what I was looking for in the LabVIEW is the scripting part when I just put text, but this is because I have actually some experience in the HDL and in the Python and the C, and I'm used to express myself in this scripting language.
Kind of like helped me to understand how something abstract like developing an algorithm could be applicable to a real application.
And I think I learned a lot. I plan on taking it back home and doing more with it.